Sofron's here to talk to us a little bit about hacking Wi-Fi.
Yeah, go ahead. All right. Hello, everyone. Hope you're having fun at DEF CON so far. I am Sofron, George Chatzisofroniou. The presentation is about breaking Wi-Fi Easy Connect. It's a quite theoretical topic, I should say, right? So we don't have a lot of implementations here. It's about attacking an abstract protocol, right? A popular protocol, and a lot of theoretical ideas around it. So a few things about me. I have conducted manual security tests, penetration tests for multiple Fortune 500 companies across the world. I've been focusing on Wi-Fi security for more than 10 years now. I have published some novel association techniques. These are, Wi-Fi association techniques. These are usually techniques that enable an attacker to gain a man-in-the-middle position in Wi-Fi. So think of karma, for example, right? How many of you know the karma attack? Raise your hand. Okay, I see some hands here. So the karma attack, coincidentally, right, that was 20 years ago when it was first released. It no longer works, right? So devices will no longer send these directed probe requests. But there are other techniques that work, such as known beacons, for example. I'm also the author of a quite popular framework, open source framework, that combines Wi-Fi association techniques with some phishing strategies called Wi-Fi Fisher. All right, so what is the talk about today? It's about breaking a Wi-Fi protocol, a new Wi-Fi protocol called Wi-Fi Easy Connect. Wi-Fi Easy Connect, the purpose is to replace WPS. How many of you guys know WPS? Please raise your hand. Okay, most of you do, perfect. So in simple terms, right, what is the purpose of Wi-Fi Easy Connect? The idea is that passwords are too complex to remember for Wi-Fi networks, right? We're too lazy to remember them. So let's make this easier, and that's what Wi-Fi Easy Connect aims to achieve. Instead of remembering the passwords, let's scan a QR code to connect to a device, to a network. Let's use Bluetooth or NFC. That's the main idea. We don't want to remember the password of the WPA2 network, so let's use something easier. And that's what Wi-Fi Easy Connect is trying to solve. And as you can imagine, right, there is this balance between usability and security that comes into play. So think of Wi-Fi Easy Connect as a layer on top of your existing WPA2 infrastructure, right? So you still have your WPA2 network, password protected network, and Wi-Fi Easy Connect is a layer on top of it that facilitates, some easier onboarding for devices. It supports multiple bootstrapping methods we discussed, like scanning a QR code, NFC, Bluetooth. Now, at the same time, right, this is a very usable protocol, but it introduces some security features. It adds security, enhances security, at least compared to WPS. That's the idea, right? In theory, that was the idea of it. It is based on the protocol behind, let's say, Wi-Fi Easy Connect technically is the certification, right? So you have the certification, and the underlying protocol is device provisioning protocol. Now, in this presentation, I will be using these terms, Wi-Fi Easy Connect, DPP, device provisioning protocol, as they mean the same thing, right? So it's the same protocol, same idea. When I say Wi-Fi Easy Connect or device provisioning protocol, I mean the same thing. Now, we use public key cryptography, elliptic curve cryptography for all of the cryptographic operations for Wi-Fi Easy Connect. The certification is currently limited, I should say, right? So we have 32 certified devices. Last month that I checked, it was only 32 certified devices across 12 vendors. But this is a popular protocol that is supposed to replace WPS, so we're expecting more vendors to implement this in the future. The same way as we expect people to move from WPA2 to WPA3, right? And it's the same organization, it's Wi-Fi Alliance, that introduces both protocols, WPA3 and Wi-Fi Easy Connect. As of now, we see Wi-Fi Easy Connect mostly used in Android devices and partial implementation, as you say, right? It's the initiator mode only. Now, we will discuss what initiator mode is. So there's some basic theory that we will have to cover, right, before digging into the attacks. The attacks are fairly simple, right? The challenge is understanding how the protocol works, understanding the specification, deciphering the specification. That was one of the challenges, right, for discovering these attacks. So to the left, we have three different pair of roles here, right? And the Wi-Fi entity can have three distinct roles from these three pairs, like at the same time, simultaneously. So to the left, we have the typical IEEE 802.11 roles, which is the station and the access point. The station can be your mobile device, your laptop, anything that connects to Wi-Fi. And the access point, obviously, can be your wireless router, right? What provides access to a Wi-Fi network. And the idea is that the station connects to the access point. This is, pretty basic knowledge for Wi-Fi networks. Now, to the right, we have the set of roles that are specific to Wi-Fi Connect. So we have the initiator and responder roles. And this is basically who speaks first, right? Is it the device? Is it the access point who speaks first? So Wi-Fi Connect supports both options. And then to the right, we have the configurator and the enrollee. The configurator is the entity, the Wi-Fi entity that provides the credentials, the WPA2 credentials to the enrollee. Because again, that's the idea here. We don't want to remember the WPA2 password. We're looking for a way to exchange the WPA2 password without remembering it. So it's stored somewhere on the access point side, and we want to transmit it in an encrypted fashion without having to type it, right? That's the idea here. So the configurator is the entity that provides these credentials to the enrollee. And again, we can have multiple combinations. We can have a station that is a responder and an enrollee, for example. Now, what are the phases of Wi-Fi Connect? We start with the bootstrapping, right, to establish some trust. And this is what we said, right? We have different bootstrapping methods. We have the QR code, we have NFC, we can have Bluetooth, or we can have something called PKEX, right, which is a Wi-Fi sub-protocol within the Wi-Fi Connect protocol that works like that. The exchange public keys, and that's the idea. The purpose of the bootstrapping phase is for the two entities to receive each other's public key. So the initiator will receive the public key from the responder will receive the public key from the initiator, right? These are not the credentials. These are the public keys that they will use in the next phase, in the authentication phase, to authenticate each other. Now, this whole process, as we go through the phases of Wi-Fi Connect, this can happen in milliseconds or it can happen after hours, right? Maybe they have done the bootstrapping phase and then after hours they decide to authenticate. So you can have, a configurator basically providing credentials to an enrollee afterwards. So after they received each other's public key, they proceed with the authentication. They basically leverage the public keys to establish a symmetric key. And that's a very common practice, right? If you are familiar with SSL, that's what we're doing in cryptography. We're using asymmetric cryptography to establish a symmetric key for efficiency. So when they have established the symmetric key, the next phase is the configuration, which is basically agreeing which will be the configurator and which one will be the enrollee. And this is, a sub-protocol within the actual Wi-Fi Connect protocol. After they agree on that, they will be, the configurator will be sending something called the connector that includes the credentials for the WPA2 or WPA3 network. So that's the idea. These are the four sub-protocols within the Wi-Fi Connect protocol. All right, now, regarding our methodology today, right, we have 3 steps. Reconnaissance phase. We want to be able to identify valid Wi-Fi Connect networks, and at the same time, we want to know the stations that connect to this Wi-Fi Connect network. And that's the reconnaissance phase. That should be pretty easy, right? I would say that the difficulty is incremented here. So the reconnaissance is probably the easiest step, right? So then, how can we access a Wi-Fi Connect network? That will be our second challenge for this talk. And finally, owning the Wi-Fi Connect network. Now, what's the difference, right? If we access the network, have we owned the network too? Well, no, that's not how it works in Wi-Fi networks. Owning a Wi-Fi network means that we are becoming the access point. We are becoming the configurator. We are able to get man-in-the-middle position for all the devices connected to that network. That's what owning a network means. So we don't only want to compromise, access the network, but we also want to force all wireless clients to connect to us, right? We are the router, basically. We are the configurator. We are provisioning the credentials. That's what own means, which is obviously the most difficult task. All right, let's start with the Reconnaissance. For discovering active Wi-Fi Easy Connect networks, the easiest way is sniffing beacon frames or probe responses. So they are advertising the DPP AKM, right? So that's a fairly simple way to identify valid Wi-Fi Easy Connect networks. Now, for identifying the stations, right, that connect to this Wi-Fi Easy Connect network, this is a little bit more challenging. And the reason is that Wi-Fi Easy Connect includes a private introduction protocol, a privacy enabling protocol, which is cool, right? It's very cool that Wi-Fi Alliance decided to implement this privacy enabling feature so that when a station connects to a Wi-Fi Easy Connect network, that's not, apparent to all the nearby devices. It's not obvious, and it's not something that an attacker can, sniff the traffic and identify that, oh, this connection is happening. So let's see a little bit how this works. So now we have these 4 sub-protocols, right, that I went through earlier. This particular attack that we will be discussing is on the network access phase of the Wi-Fi Easy Connect protocol. So what happens here, right, the private introduction protocol, the initiator will send a private peer introduction message, and the responder will reply if the responder supports this privacy enabling feature with a private peer introduction notify message. And if that works, the connector that includes the credentials for the network will be transmitted encrypted, right? Again, very cool feature from Wi-Fi Alliance. We want this type of privacy when we're connecting to Wi-Fi networks. Now, the problem here, right, and that's a very simple attack, is that an attacker can block this message, right? And here I want to, let you guys know, in case you're not very familiar with Wi-Fi security, blocking messages, it's quite simple, right? Using commodity hardware, using techniques such as reactive jamming, it's very trivial for an attacker to block a Wi-Fi frame, a wireless frame, right, from reaching the destination. By doing that, we are enforcing the less secure, the less private protocol, a typical peer discovery request. And the responder will reply with a peer discovery response, and they will use the unencrypted protocol, which, as you can see here, that's how a connector looks like, right? Most of the data here is encrypted, but as you can see, the SSID, the network that the station tries to connect, is unencrypted, right? So even though it's very cool that Wi-Fi Alliance introduced this protocol, the way to bypass and circumvent this control is very, very trivial, right? Are you guys curious what Wi-Fi Alliance responded to this finding when I disclosed this to them? Let's see. So they consider this an acceptable risk. Apparently, circumventing the private introduction protocol is basically privacy exposing. Whoa, right? Good for them. I mean, they're willing to take risks in life. All right, what we are recommending? We are recommending that future versions of the specification should validate the preferences, right, in subsequent exchanges. So basically, we want these 2 entities, after they finish this first interaction, right, we want the station to say, hey, I originally wanted to connect with you using this private protocol, right? And the access point say, hey, really? Because I received a message that you wanted to connect with a simple, non-encrypted protocol. That means that someone was man in the middle of our connection, right? And abort the connection. It's a very simple remediation control. All right. And that's all we have to say about Reconnaissance, right? By downgrading to the weaker, simple protocol, we can identify valid stations, and we can also, just easy identify Wi-Fi Easy Connect network by looking at the advertised DPP AKM. Now let's discuss a little bit about how we can access Wi-Fi Easy Connect networks. And for that, we will go to the bootstrapping phase of the protocol, right? As a reminder, we have multiple bootstrapping methods. We have Bluetooth, we have NFC, we have QR code. Well, there is one called PKEX that I briefly discussed earlier. This is a Wi-Fi sub-protocol within Wi-Fi Easy Connect. Again, the idea of Wi-Fi Easy Connect is that we're too lazy to remember long passwords, so the PKEX is using short numeric codes, right? It's kind of like WPS PIN, if you remember that. Just short numeric codes instead of a long, complex password. And this is irony right here, because I don't think it's really hard to remember long passwords. And we're using elliptic curve here. So the thing is that in order for PKEX to work, right, the initiator and the responder, they need to agree on a cryptographic group. That's a set of points, right, for elliptic curves. They need to agree on the elliptic curve that they want to use. And that's the first thing that they're doing. Before they start doing any cryptographic operations, they need to agree on a group. So the initiator originally has a list of preferred groups, right, with an order of preference. The initiator will propose a cryptographic group, and the responder can either accept the group if they also are willing to use that group, or they can propose a different group, downgrade to a different group if it doesn't support the proposed one. Here's how it works, right? So you can see to the left the list of preferred groups for the initiator. You can see the list of preferred groups for the responder. So the initiator will start with the first preferred group from on the list, right, which is group 26. So it will ask group 26. The responder does not support group 26, as you can see. So it will propose their own preferred group instead, which is group 30, right? And the initiator does support group 30. So they will agree on group 30 here if everything goes well. Here's what could go wrong here. An attacker can block that message from the responder for group 30 and instead impersonate the responder and send a message that they want group 27. Now, this impersonation works because we're in the very early phase of the protocol. They haven't exchanged public keys yet. They haven't, so all of these messages are unencrypted. It's possible for the attacker to impersonate the responder because they have not established any trust yet, right? So the attacker blocks the message using reactive jamming techniques that we discussed, right? And then send a different group, group 27, that both initiator and the responder have in their list, but it's their the least preference option. So that's a group downgrade attack here by forcing them, you know, because the initiator will say, yeah, I have group 27, and they will agree on group 27, which is their least preferred option here. So what we have here is that the group negotiation lacks cryptographic safeguards. We have seen these safeguards in WPA3, but they don't exist in Wi-Fi Easy Connect. A weak group selection means weaker Diffie-Hellman exchange, which also means an easier brute forcing. And there are also reasons for someone, right? Some very paranoid users, they want to avoid certain groups, certain cares, because they believe they have been backdoored, for example. But in all honesty, right, in a typical Wi-Fi penetration testing, exploiting a weaker group is quite uncommon. So this is mostly applicable for, you know, strong adversaries, nation-state threat actors. But it's still something for the protocol that is supposed to be widely used. This is quite important. Wi-Fi Alliance said that this will take this matter under discussion to decide a group of action. I haven't heard back from them, but yeah, hopefully they will decide to fix this. It's not like the fix is difficult, right? What we're recommending is that in a later phase, in a commit reveal phase, they just verify, you know, the initiator and the responder, they share their preferred groups and say, hey, I wanted to connect, I wanted us to use that group, right? So why did we end up using that least preferred group? That's all it takes, right? It's not something more complex than that. And if there is a protocol, if there's a mismatch, then the protocol needs to be aborted because someone is conducting an attack in this wireless range, in the wireless range, right? Right. Again, that's not very easy to be conducted in a typical Wi-Fi penetration testing, right? So we're looking for something easier here. And for that, let's go to the authentication phase of the protocol. Now they have established, they have exchanged some public keys. And let's see how this authentication protocol works. What I found out after reading the specification is that apparently Wi-Fi Easy Connect is supporting mixed authentication. And that was quite surprising, I'm telling you, because it wasn't clear, right? When I was reading the specification, it wasn't clearly stated that Wi-Fi Easy Connect supports a mixed authentication, that, you know, different provisioning methods provide different level of security. it was something that I had to decipher. And again, that's the challenge when we're reviewing these Wi-Fi protocols and specification. The challenge is deciphering what Wi-Fi Alliance is trying to say. So what we have here is that some of the devices obviously support only have partial implementations, like we discussed about Android, right, that only have the initiator mode. And we can have system administrators, network operators that enable multiple provision modes. So you can have QR code and PKEX for the same Wi-Fi's in network at the same time. And that would be fine if they would provide the same level of security, but they are not, right? They provide different level of security. Some provisioning methods skip mutual authentication. So you can have mixed authentication modes. So that means that we can have an initiator that is having the typical mutual authentication method, right? But we can have another initiator that only has responder authentication. The initiator is never being authenticated. And the one bootstrapping method that is vulnerable, right, that only supports single-factor authentication is the QR code. So when you are scanning a QR code to connect to a network using Wi-Fi as a connect, you would expect that, you know, the client, that your mobile device, uses a certificate from the secure enclave part of your phone, for example, but that's not the case. There is no authentication for your device. When you are scanning a QR code, your device is never being authenticated. You can use that QR code and enroll as many devices as you want. The responder, the configurator, the access point will never know, which device is connecting to their network, right? You just have an open door there. As soon as you have that QR code, you have an open door. So the idea here is locating that QR code. And locating that QR code can happen with sniffing the DPP authentication requests. There is a way to conduct Wi-Fi triangulation, right? So if you're doing a red teaming, for example, you want to locate that. Sometimes this QR code is very visible, right? It's somewhere, organizations, they sometimes, hang it on a wall somewhere. And it's very trivial to locate that QR code, and that's an open door again, right? There's no authentication from the station side. You can enroll as many devices as you want, as long as you have this QR code. But in case this QR code is somewhere hidden, you can use triangulation techniques to identify the physical location of that QR code. So that's an interesting outcome from this, that the QR code method is basically an open door. And the reply for Wi-Fi Alliance is that yes, this is a policy decision for the deployed enrollee, which means that Wi-Fi Alliance seems to be aware of this in a way, and they seem to accept the risk. But that's a problem. Like intended mixed authorization modes might help for flexibility, but flexibility can backfire. And if we rely on the network operators that they don't have the proper security training, right? They don't have the proper knowledge to do threat modeling, for example, then it's very expected, I should say, to have misconfigured Wi-Fi to connect networks. So you could have a network that supports both PKEX and QR code. Well, the QR code circumvents the mutual authentication, while PKEX is not. So what we're looking for here is a strict mutual authentication mode. When we're saying mutual authentication, we mean mutual authentication. That means that the clients connecting to the Wi-Fi to connect network, they should send a certificate that is now stored on the other side and is expected every time they connect. All right, and that's for gaining access, right? If we find a QR code, we can't get into the network. But now the most challenging is how can we own a Wi-Fi to connect network? How can we actually force wireless devices to connect to our own malicious configurator? Let's go back to bootstrapping, and we're still staying on the QR code method here. One way is to simply do a QR code evil twin, right? Because you cannot authenticate a piece of paper. If they rely on a piece of paper, right, to connect to a conference Wi-Fi, that can be very easily, duplicated by an attacker, and you cannot know which one is the valid one. So that's a very trivial method. You cannot rely on a piece of paper or a device for authenticating to a Wi-Fi to connect network. Another way, PKEX code reuse exploitation. And here, that was also something that was found on host APD. We have a CVE for this. And the idea here is that PKEX codes, right? Again, as a reminder, PKEX is one of the bootstrapping methods along with Bluetooth, along with NFC. And what we found is that these codes, they should not be reused, right? But on host APD, they were not deleted. They would keep use the same code for many different devices that want to connect to the Wi-Fi Connect network. They would use the same public key, the same code for different public keys that were generated. And that's a way for an attacker to masquerade as a legit responder. So let's see how this works, right? For PKEX, they will generate an ephemeral key pair. So capital X is the public key, lowercase x is the private key. And they will encrypt the public key, right? The responder needs to receive that capital X, that public key. They will encrypt it. That's what addition does in elliptic curves, right? With the hash of the code, they already have exchanged the code out of band, right? That's the idea. That short numeric code, they both know that short numeric code. So the initiator will send a PKEX exchange request with encrypted now public key, and the responder will, as they know the code, they can generate the hash, they will subtract it, and they can get that public key. What could go wrong here is that an attacker can block that message from reaching the target. And again, they haven't established any trust yet, so the attacker can impersonate the responder as needed. So they will retrieve the value X, the public key. They will reply back as normal as a responder, continuing the bootstrapping, as an attacker would do, because the attacker also knows the code at this point, right? And they will proceed with the rest of the protocol, authentication, configuration, network access. So that we can say that this is like a PKEX evil twin type of attack. Now, this is not a specification issue. That's just something that we expect vendors to implement it wrongly, let's say, like host APD did that. But this is expected that other vendors might implement it wrong for usability reasons. Also, users tend to reuse codes all the time, right? So that's a technique for misconfigured networks, not exactly an attack against the specification. All right, still not easy, right? Because the techniques that we discussed for owning the network, like QR code, duplicating a piece of paper, right? That requires some user interaction, some social engineering to enforce the victims, users, to actually scan that QR code. But also, that later technique, we need to know the code, right? It has a little bit of technique regarding reacting faster than the legitimate responder, but we're looking for something better that doesn't rely on PKEX only. So for that, we will have to go to the configuration sub-protocol of Wi-Fi Connect. And the way that this works is that we have done the DPP bootstrapping, so both entities have exchanged their public keys. We have done the DPP authentication, so using these exchanged certificates, they have established a symmetric key, in this case called symmetric KE. And the enrollee, right, for the configuration protocol, the enrollee will send a DPP configuration request where they include their role, right? The enrollee will say, hey, configurator, I am actually an enrollee, and I would like to get some configuration, right, with all the data that I need, all the configuration data that I need to connect to that Wi-Fi Connect network. And the configurator will happily provide that. The configurator will happily say, okay, here you go. And all of these are encrypted with a symmetric key that they have established in the previous phase. What could go wrong here? The attacker, who has already exchanged public keys, can lie and say, hey, I'm not actually an enrollee, I'm a configurator like you. Because this is something that is supported by the Wi-Fi Connect protocol. it is possible to have multiple configurators in a Wi-Fi Z Connect protocol. Think of a Wi-Fi Z Connect that's quite large in a conference like DEF CON. You can have multiple configurators. So it is possible for a malicious enrollee, right, to pretend that they are a configurator, not an enrollee. All they need to do is to change that value, the net role value. And instead of asking configuration data as they are enrollee, they are asking configuration data as they are a configurator. And in this case, the configurator will reply back with the DPP envelope data. Now, all these are encrypted with that symmetric key, but they have established that symmetric key, right? So we're talking about a malicious enrollee here, someone who has already joined the network, right? And they want to do what we call in security, right, privilege escalation, elevate their privileges to configurator. So the DPP envelope data that the malicious enrollee will receive is a very interesting file that is used for backing and restoring configurator credentials. It is used for having multiple configurators in a Wi-Fi Z Connect DPP network. Its management is vendor specific, so this could be stored locally in some cases or can be stored in memory. And the idea is that it's using a typical password-derived key encryption, symmetric encryption, right? So you can decrypt this envelope and own the network, and you can do that by conducting a very typical offline brute force attack. Now, this is, if you ask me, this is ridiculous, right? In 2025, having a protocol, a Wi-Fi protocol that is susceptible to an offline brute force attack, right, should not be the case. You would guess that we would have learned our lesson from WPS, from web, from all these previous protocols, but apparently we haven't. So it is possible to capture that DPP envelope data because the enrollee will pretend that they're a configurator, they will receive the DPP envelope data and conduct a typical offline brute force attack. And the brute force can work very easily as part of a dictionary attack. So you basically iterate through a list of passwords, you calculate the hash method is PKEX, but it is an offline brute force attack. You can easily do that. And if you decrypt that message, if you decrypt that package, you will gain access to something called the privacy protection key. And this is the key to own everything. Like this key will make you the equivalent of domain admin in a Windows domain, for example. Because the privacy protection key is the key that's shared across configurators, and is the one that is used for signing these connectors that include the Wi-Fi credentials. So by getting this key, you can actually issue fake network configurations for all the clients, right? And basically own all the clients in a Wi-Fi Z Connect network and send them push fake rogue configuration files to all of them. And you have one bad configurator, that's a global compromise for the rest of the Wi-Fi Z Connect network. So simply by impersonating, right, by impersonating a configurator and changing that value, you can do a global compromise of the Wi-Fi Z Connect network. This is the Wi-Fi Alliance response, right? Wi-Fi Alliance will consider other methods because right now that envelope data, that very sensitive file is only protected by a password. So they will consider other methods in addition to the password method, which is considered an acceptable risk, right? Crazy. What we are recommending here, obviously we don't believe that this is a sufficient fix in any way, right? Again, in 2025, there should not be any wireless protocol, any Wi-Fi protocol that is susceptible to an offline brute force attack. And as long as the password method is still supported, the envelope data remains at risk, and the privacy protection key that is included in that envelope data remains at risk. So what we're recommending here is very trivial, right? Authorization checks. When someone says that they're a configurator, don't believe them, right? They might be an enrollee acting as a configurator. It's very simple. So we want an authorization logic, not authentication. We are past the authentication phase. We are past the authentication phase and we're looking for authorization here. We want the configurators to authorize. Are you truly a configurator or are you playing with me? That's what we ask here, right? Validating the enrollee identity against some policy-based control. The other thing, right now we have the PPK, the privacy protection key, which is a single point of failure. Accessing this key, like with the exploit that I just presented, owns the whole network. And that's not gonna work. Like, we should have different separate configurator keys for each configurator, not a single point of failure. And another thing that's not mentioned on that slide is that this key cannot be revoked, right? So you have lifetime access to the network. Even if you change the WPA2 or WPA3 password that you are basically trying to protect, right? The PPK remains static. It's a static key, right? You will still have lifetime access, right? If you have that Wi-Fi network for 10 years and you have a policy to change this for every year, for example, well, the privacy protection key remains static. It's a single point of failure. So what we're looking for here is also revocation methods for the privacy protection key. All right, so we discussed a number of different attacks here that were targeting different phases of the Wi-Fi Easy Connect protocol. What is also interesting, in my opinion, is that some of these attacks are applied to the initial release, can work against the initial release of the specification, but can also work to some of them were introduced, I should say, in subsequent versions of the protocol. And I think that's interesting because what I believe is happening is that vendors are keep pushing for more usability-oriented features. So the vendors will ask and ask for more usability features. Like, let's make things easier for everyone. Let's make things easier for the user. And that's exactly the problem here, right? Because Wi-Fi Alliance will eventually have to sacrifice some of the promises that they originally made. They will have to sacrifice some of the assumptions that they made on their threat model in order to satisfy these vendors. So some of the attacks, like the configurator impersonation that we just discussed, right? That a very simple technique to own the network. That was introduced in a later phase of the protocol. And our understanding is that this happened because vendors are keep pushing for more features that favor usability. It is always this delicate balance between usability and security, particularly in these type of protocols that, you know, try to make things easier for everyone. All right, conclusions. We have several protocol level vulnerabilities that are specific to the DPP design, right? Again, this is a very theoretical research at this point. The idea is that this is a specification that all vendors that want to implement and get this certification from Wi-Fi Alliance, they will implement this specification and they will be vulnerable automatically, right? If they follow this specification, they will be vulnerable to the attacks that we discussed today. Now, the migration from WPS to device provisioning to Wi-Fi Easy Connect, does it really making things more secure? Doesn't seem so. What I'm seeing is that we're shifting the burden to network operators. The risk management is now up to the network operators. They are the ones that will decide what provisioning methods they want to support. They will decide, I want the PKEX method, I want the Bluetooth method, without even knowing that these provide different levels of security. Or, for example, how they're going to distribute their QR codes. That's really up to them, how they're going to protect these QR codes. Because as we said, these are, you know, an open door that you can easily access the Wi-Fi Easy Connect network. So we're relying now on network operators who they don't have the proper security training for the deployment of Wi-Fi Easy Connect networks. We have a lot of usability-driven enhancements, what we discussed, right? So the subsequent versions of the protocol have actually weakened the protocol's security posture. New vectors for abuse, right? Mixed authentication modes, particularly when this is something that is not clear after reading the specification. It's not clear that mixed authentication modes are possible in Wi-Fi Easy Connect network if you deploy multiple provisioning methods. Lack of revocation mechanisms. That PPK is a single point of failure and you cannot even revoke it. You will have to reboot the whole protocol, right? But without having the proper knowledge and understanding of how the protocol works, why would you do that? That's super important, right? For critical keys like the privacy protection key that allows you to issue configuration files for all the devices, revocation mechanisms is very surprisingly that they're missing for this critical key pair. And then, as we said, right, we don't have the required training. We need the required training for protocol adoption for our network operators, for the Wi-Fi operators, and clear provisioning policies too, right? So if someone claims that they are a configurator, we need to be able to authorize this request based on a policy. Is this station really a configurator or not? That's the question here. That was everything I had. Hope you enjoyed the talk. Thank you very much for listening.